Hello everyone. In this segment we'll discuss about the new technique called as Fourier Transform. Now friends, as far as the name is considered, transform, that is any technique that changes from one end to another end, probably from one domain to another domain, that techniques are called as transform technique. Now here we have the term as Fourier Transform. So in earlier videos we have discussed about an important technique which is called as Fourier series. There we have seen Fourier series representations are used for periodic signals. Now what about non-periodic signals? So in case of non-periodic signals, their representations or their analysis is done with a technique called as Fourier Transform. Now in case of Fourier Transform, or in case of any transformation technique, we generally switch from time domain into frequency domain. Now, why it is necessary to switch any signal or to convert any signal from time domain to frequency domain is it is quite easier to analyze the characteristics of any signal in frequency domain in comparison with time domain. Therefore, we have several techniques like Fourier transform, Laplace transform, Z transform is there, fast Fourier transform is there, DFT is there. Now, as far as Fourier transform representation is considered, if we have an input signal which is continuous x of t, its Fourier transform representation will be x of j omega, where omega is the frequency component. So again we are switching from time domain to frequency domain. As far as its mathematical derivation is considered, we can write Fourier transform of x of t will be integration, input term is x of t into its exponential term as e raised to minus j omega t into dt. So this will be the mathematical expression for representing Fourier transform. Similarly, if we have x of j omega as Fourier transform, its inverse Fourier transform will be x of t. That representation will be x of t will have a formula as 1 upon 2 pi, because we are covering the range from 0 to 2 pi. Integration, we have now x of j omega into, here we have a minus term, here we will get this term as e raised to plus j omega t into d omega. So this will be the expression for Fourier transform and inverse Fourier transform. Now if it is Fourier and inverse Fourier transform techniques, whenever we will represent x of j omega, it is definitely a complex term because j is there. So whenever we are having a complex term, it can have a real term, that is xr j omega, plus its imaginary term as xi j omega. It is as good as representing x plus I y, xr plus xi. Now whenever we will get the complex term or a complex number, it can have two components. One is known as its magnitude term as mod x of j omega, that I can represent as square root of a real plus square of real term plus square of imaginary term. So it becomes xr square j omega plus xi square j omega. So based on that we can draw magnitude spectrum of the given signal. Similarly, when I come across its phase spectrum, which I can write phase or angle of x of j omega is equal to, we have that standard notation that is written as tan inverse of imaginary number divided by real. So we have imaginary term as xi j omega divided by real term as xr j omega. So in case of analysis of signals are considered, two important terms are there. One is magnitude spectrum and one is its phase spectrum. So this is about the representation of Fourier transform. Let us consider one example on the same, as find Fourier transform of the given signal, which is given as x of t is equals to del t. So we can write Fourier transform equation now. x j omega as integration. This is our single x of t and exponential term as it is. Now let us put del t over here, so we'll get del of t into e raised to minus j omega t dt. Now this is an impulse function, and we know the property of impulse function, it exists only for a single value of t, that is at t is equals to 0, del 0 will be equals to 1, and otherwise its value will be 0. Therefore we'll get x of j omega is equals to, there will not be any part of integration because we have a single value of t0, so we'll get this term as del 0. If I put it here as t0, we'll get this term as e0. Now e exponential 0 will be 1 and del 0 is 1, so the product will be 1. Therefore its Fourier transform becomes 1. Now if it is 1, it is a real number, and if it is a real number, there is no point of drawing its phase spectrum, so only we'll get its magnitude spectrum, and that will have a value as 1 for the entire range of omega. So let us draw its phase spectrum. On x-axis we'll put the variable as omega, and on y-axis we have mod x of j omega. Now the value is 1, so this is constant line we'll draw having an amplitude 1. So this will be the magnitude spectrum of the given function del t. Let us take one more example. X of t is equal to e raised to minus 8 into u of t. So here we have kept this value. Now we have an input function as that is going to be a step function. So if it is a step function, we can change the limit from 0 to infinity. This is e raised to minus j omega t. So we are left with e raised to minus at, e raised to minus j omega t into dt. So the base is same, I can add the power terms, we'll get this is e raised to minus a plus j omega t we have taken as common into dt. Now let us integrate this term. So the integration of exponential e raised to minus a plus j omega t divided by minus a plus j omega over the limit 0 to infinity. Let us take this term outside, minus 1 upon a plus j omega. Upper limit, if I put infinity, this is a minus sign, we'll get e raised to minus infinity minus e raised to 0. Now e raised to minus infinity will be 0, and this is going to be 1. So this is minus minus plus, we'll get x of j omega as 1 upon a plus j omega. So this is Fourier transform of this exponential function. Now let us draw its magnitude and phase spectrum. So for drawing the magnitude spectrum, we'll write the term mod x j omega will be equals to 1 as it is, square root of 1 square will be 1 upon under root. Now we have real term a and imaginary as omega, so we'll square the terms, a square plus omega square. Similarly, if I come across phase mod x j omega, it will be, now if I take, this is real number and its phase will be 0, and this is a complex number, so we can put this sign as minus. Why minus? Because this term is in denominator, and when we are taking its phase spectrum, this will be 0 minus this term, that will be minus. Tan inverse of imaginary term we have omega, real term we have a, so this becomes omega divided by a. Now let us try to draw this magnitude spectrum. Now here the variable is omega, so we can take any value of omega. So for that case, let us suppose we will put the value of omega in this range. This is the magnitude of x of j omega. We can fetch the values. Suppose we are getting it for 0, plus 1 and minus 1. probably you can take more values. I am taking only 3 samples, 0, +1, -1, and a, suppose a we are taking as constant, that is going to be 1. You can take any value, only for understanding purpose I am writing this as. Now when we put the first value omega 0 in this equation, we will get this value as xj0 is equals to 1 by under root omega is 0, so we will get only a square, that will be 1 divided by a. We have considered a as 1, so I can get this value as 1. Similarly for 1, this will be 1 upon under root a square is 1 plus 1, that will be 1 by root 2. That value will probably 0.707. So this is 0.707. Similarly for -1, as it is a square term, 1 plus 1 again same, 0.707. Now if you analyze this carefully, this is omega square. So even if I take omega value negative or positive, the result will be same. The magnitude is going to be same. Now based on this value, let us draw its magnitude spectrum. I am keeping this as a reference. Here we will take x-axis parameter as omega, and on y-axis we have magnitude mod x of j omega. Now for the first value, that is at omega 0, we are getting magnitude as 1, which is going to be maximum. Here we are getting this term as 1. Next we will plot. For 1 we are having 0.707. Suppose this is 1, so we are getting something around 0.707, so I can take near about this value. You can plot it using a scale also. Similarly for -1, the magnitude is same, so we can have this term. Now as far as omega value goes on increasing, definitely the magnitude will fall, and at infinity definitely it will approach to 0. So based on that, if I try to draw, it will be 0, then it rises, it approaches to 1, again it fall downs, and it fall downs, it approaches to 0. So you can get a magnitude spectrum like this one. So this will be its magnitude spectrum. You just take more number of values, and based on that you will get a smooth curve for magnitude spectrum. Now let us come across the phase spectrum, which is given by, I am writing it here for the reference. This is minus tan inverse omega upon a. Now in order to draw this one, instead of putting so many values, we can predict the phase spectrum by the two values. The first value, when we have omega, that is going to be 0. Now when omega is 0, tan inverse 0 divided by anything will be 0, and tan inverse of 0, the angle is going to be 0. Similarly, when I put omega as plus infinity and omega as minus infinity, now when we put omega as infinity, this term will be tan inverse of infinity. Now how will you get tan inverse of infinity? So as you know that tan theta is basically a ratio of sine by cos. Now in order to get this term as infinite, definitely the denominator should be 0, and we know that when theta is pi by 2, cos pi by 2 will be 0, and anything about 0 is going to be infinite. So if I want tan inverse of infinity, definitely the angle is going to be pi by 2, provided that this minus sign will keep, so this will be minus pi by 2. Similarly, when I want minus pi by 2 or minus infinity, this is going to be minus pi by 2, and this minus will definitely be plus pi by 2. Now if I got these three terms, I can sketch the spectrum. This is omega. Now when it is 0, the intersection point is 0. This is angle x of j omega. Now when I consider omega as plus infinity, our angle is minus pi by 2, so definitely below this axis. So let us see, this is the line for minus pi by 2, and when omega minus infinity, this in this term, this is, I'm putting it as plus pi by 2. So for omega minus infinity, definitely it will start from plus pi by 2. This will be the axis, or this will be the term, and it approaches to 0. And for omega plus infinity, it will move on to the plus infinity term. Now if I take any value between minus to plus infinity, definitely the range will be covered here and here. So if you join this line carefully, we can get a slope like this one. So this is known as the phase spectrum. I hope you understand how to draw magnitude as well as phase spectrum. If you understood this term, let us take one more example for your clarification, so that it will be easy to understand. Let's suppose we have the third function as x of t is equal to, I'm taking it as signum function. So if it is a signum function, I'm putting it directly x of j omega minus 2 plus signum function into exponential term into dt. Now we know the property of signum function. It has an amplitude 1 for t greater than 0 and minus 1 for t less than 0. So if I split this integration term, first from minus infinity to 0, that is for all negative values of t, signum function value will be minus 1, this exponential as it is, plus when I put it from 0 to plus infinity, for all positive values the amplitude is 1, so 1 into e raised to minus j omega t dt. Let us integrate this term now. We'll get e raised to minus j omega t by minus j omega, limit as it is. For this also, e raised to minus j omega t minus j omega 0 to infinity. So I'm taking this as minus 1 by j omega, upper limit 0 and lower limit minus infinity. So based on that, we'll get this term only as 1. Similarly, minus j omega, this upper limit infinity, and this is 0. So we'll get this term as minus 1. How we have kept this value already we have seen in the previous example. So this will be just a recorrection over here. If I put it 0 over here, plus and minus infinity, this is upper limit and this is 0, and we are left with this minus sign also. So this minus becomes plus. So we'll get this as 1 by j omega, this is plus 1 by j omega. So our answer will be x of j omega is equals to 1 divided by, or we can take j omega as common, so we'll get 2 divided by j omega. So this will be the Fourier transform of this function. I hope you understood the concepts. Thank you.